Welcome to Chapter 12, where we'll explore one of the fastest-growing inspection technologies used throughout modern industry: thermal or infrared testing. Infrared thermography is a non-contact inspection technique that allows us to visualize temperature differences across the surface of an object. Unlike many conventional NDT methods that require direct contact with the component or reveal only existing discontinuities, infrared testing enables inspectors to detect abnormal thermal patterns that often indicate problems long before catastrophic failure occurs. Throughout this chapter, you'll discover that infrared testing is much more than simply taking pictures with a thermal camera. It is a scientific method based on heat transfer, electromagnetic radiation, and the thermal behavior of materials. Understanding these principles is essential, because an infrared image only tells part of the story. A skilled thermographer must interpret what the image actually represents and determine whether an observed temperature difference indicates a genuine defect or merely an effect of the surface condition. Infrared thermography has become an indispensable predictive maintenance tool across many industries. Electrical inspectors use it to identify loose electrical connections before they overheat and fail. Mechanical maintenance teams detect bearing problems, lubrication deficiencies, shaft misalignment, and excessive friction. Process industries monitor furnaces, pressure vessels, insulation systems, refractory linings, pipelines, and storage tanks. Civil engineers use thermography to locate moisture intrusion, insulation defects, and delamination in concrete structures. One of the greatest strengths of infrared testing is that inspections can often be performed while equipment remains in service. This minimizes downtime, improves maintenance planning, and enhances plant safety by identifying developing problems before they become emergencies. During this chapter, we'll build our understanding progressively. We'll begin with the basic physics of infrared radiation, move through heat transfer mechanisms, study emissivity and other surface properties that influence measurement accuracy, examine various infrared instruments, and finally, apply these concepts to real industrial case studies. We'll conclude with certification-style examination questions to reinforce the knowledge expected in ASNT, ISO 9712, and CSWIP certification examinations. As experienced inspectors know, thermal cameras never diagnose defects by themselves. They simply provide thermal information. The responsibility for correct interpretation always belongs to the inspector. Now that we've established the importance of infrared testing, let's begin by understanding why temperature is one of the most valuable indicators of equipment health.
Before studying any inspection technique, it's important to understand exactly what knowledge and skills we should gain by the end of the chapter. These learning objectives provide the roadmap for everything that follows. We'll begin by defining what thermal or infrared testing actually is and understanding why temperature monitoring plays such a central role in predictive maintenance. Nearly every industrial process involves heat in some form. Whenever equipment begins to fail, whether electrically or mechanically, temperature is often one of the earliest measurable indicators. Next, we'll establish the scientific foundation by distinguishing heat from temperature. These two terms are frequently confused, especially during certification examinations. Heat refers to energy transfer, while temperature represents the degree of molecular motion. Understanding this distinction is essential because every infrared measurement ultimately depends on heat transfer. We'll then study the three fundamental mechanisms by which heat moves: conduction, convection, and radiation. These concepts explain why certain defects become visible to thermal cameras while others remain hidden. Another major objective involves understanding surface properties, particularly emissivity, reflectivity, transmissivity, and radiosity. These characteristics directly influence how accurately an infrared camera measures temperature. Many beginners mistakenly assume that a thermal camera measures temperature directly. In reality, it measures infrared radiation, and the surface properties determine how that radiation relates to the actual temperature. The chapter also introduces the equipment used in infrared inspection. We'll compare contact instruments such as thermocouples with non-contact devices, including infrared thermometers, pyrometers, and thermal imaging cameras. We'll also distinguish passive thermography, which observes naturally occurring temperature differences, from active thermography, where an external heat source is intentionally applied to reveal hidden defects. A practical case study will demonstrate how these principles come together during an actual inspection. You'll learn how experienced inspectors interpret thermograms rather than simply observing colorful images. Finally, we'll reinforce your understanding using examination-style questions commonly encountered in ASNT, ISO 9000, 712, and CSWIP certification examinations. Throughout this chapter, remember that successful infrared inspection requires both scientific understanding and practical judgment. Technology provides measurements, but professional interpretation transforms those measurements into reliable engineering decisions. With our learning objectives established, let's examine why temperature monitoring has become one of the most powerful tools in industrial maintenance. Temperature is one of the most frequently monitored variables throughout industry because nearly every failure mechanism generates heat before complete failure occurs. This makes thermal monitoring an exceptionally valuable predictive maintenance tool. When electrical resistance increases because of a loose connection, corrosion, or overloaded circuit, electrical energy that should perform useful work is instead converted into heat. The resulting hotspot becomes visible long before the connection fails completely. This explains why electrical inspections remain one of the largest applications of infrared thermography. The same principle applies to mechanical equipment. Components operating correctly generate relatively predictable temperatures. However, worn bearings, inadequate lubrication, shaft misalignment, excessive friction, partially blocked valves, and insulation failures all alter the normal thermal pattern. Detecting these changes early allows maintenance teams to schedule repairs instead of responding to unexpected breakdowns. The slide also highlights that infrared testing has become an important non-destructive testing technique. Beyond predictive maintenance, infrared thermography helps identify subsurface defects in composite materials, moisture trapped within insulation systems, delamination in concrete structures, refractory deterioration, and insulation failures in pipelines and pressure vessels. Notice the field experience highlighted on the slide regarding pumps and motors. Experienced reliability engineers often begin infrared surveys with bearing housings because bearing temperatures frequently provide the earliest indication of lubrication problems or mechanical misalignment. Detecting a gradual temperature increase over several inspections allows maintenance to intervene before vibration levels become severe or catastrophic bearing failure occurs. However, it's important not to rely solely on absolute temperature values. Professional inspectors compare similar equipment operating under similar loads and evaluate temperature trends over time. A bearing operating at 70 degrees Celsius may be completely normal under heavy load, while another operating at only 50 degrees could indicate a developing problem if its historical operating temperature has always been much lower. One common mistake made by inexperienced inspectors is assuming that every hot object represents a defect. In reality, many components are intentionally hot during normal operation. Successful thermography depends on understanding expected operating conditions and identifying abnormal thermal behavior rather than simply high temperatures. As emphasized for certification examinations, remember the two primary industrial application categories. Electrical systems primarily generate heat through resistance, while mechanical systems generate heat through friction, leakage, restriction, or insulation deficiencies. Having established why temperature is such a valuable maintenance indicator, we can now examine both the strengths and the limitations of infrared testing. Like every non-destructive testing method, infrared thermography offers significant advantages, but it also has limitations that inspectors must understand to avoid incorrect conclusions. One of its greatest strengths is speed. Thermal images are produced almost instantly, allowing inspectors to survey large facilities efficiently. Entire electrical substations, production lines, or process plants can often be inspected within hours instead of days. Another important advantage is versatility. Infrared testing may be performed using passive thermography, where naturally occurring temperatures are observed, or active thermography, where an external heat source is introduced to reveal hidden defects. Unlike radiographic testing, infrared inspection involves no ionizing radiation. It does not require radioactive sources or X-ray generators, making it considerably safer and easier to deploy under normal operating conditions. The technology also accommodates both contact and non-contact measurements. Contact devices provide precise point measurements, while thermal imaging systems rapidly assess entire surfaces. This combination allows inspectors to locate anomalies quickly and then verify them using more accurate contact instruments. Perhaps the greatest practical advantage is the ability to inspect large structures and operating equipment without interrupting production. This capability makes infrared thermography one of the most valuable predictive maintenance tools available today. However, infrared testing also presents important limitations. Thermal imaging equipment can represent a significant capital investment, particularly high-resolution cameras designed for industrial diagnostics. Another limitation involves reflective surfaces. Highly polished metals often reflect infrared radiation from surrounding objects instead of emitting their own thermal energy. Consequently, the camera may display temperatures that do not represent the actual surface temperature. The slide also highlights repaired areas. Whenever repairs alter material thickness, composition, weld geometry, or insulation, local heat flow changes. These differences can produce unusual thermal patterns that resemble defects but actually result from the repair itself. Experienced inspectors always document repaired locations and interpret them with additional caution. Similarly, low emissivity materials frequently require special preparation. Applying a small piece of high emissivity tape or a temporary coating allows more accurate temperature measurement by reducing reflections. A common field mistake is assuming that colorful thermal images automatically represent accurate temperatures. In reality, the image quality may appear excellent while the temperature values remain significantly inaccurate because of incorrect emissivity settings or reflected radiation. Professional inspectors therefore combine infrared testing with engineering judgment, process knowledge, and, when necessary, complementary NDT methods to confirm their findings. Now that we've reviewed the strengths and weaknesses of infrared testing, let's examine the scientific principles that make the technology possible. To understand infrared testing properly, we first need to understand where infrared radiation fits within the electromagnetic spectrum. The electromagnetic spectrum includes gamma rays, X-rays, ultraviolet light, visible light, infrared radiation, microwaves, and radio waves. Each occupies a different range of wavelengths and frequencies. Infrared radiation lies immediately beyond visible red light, making it invisible to the human eye but easily detected by specialized infrared sensors. Although we cannot see infrared radiation directly, we experience it constantly. Heat emitted by sunlight, electric heaters, incandescent lamps, ovens, and even the human body consists largely of infrared radiation. Every object with a temperature above absolute zero continuously emits infrared energy. This fundamental principle allows thermal cameras to operate even in complete darkness because they detect emitted radiation rather than reflected visible light. The lower section of the slide addresses one of the most common misconceptions encountered in both industry and certification examinations: the difference between heat and temperature. Heat is energy transferred because of a temperature difference. It is measured in joules and always flows naturally from a hotter region toward a colder region until thermal equilibrium is reached. Temperature, by contrast, is a measure of the average kinetic energy of particles within a material. It indicates how hot or cold an object is and is measured using units such as Kelvin, Celsius, or Fahrenheit. Understanding this distinction is essential. A thermal camera does not measure the amount of heat stored in an object. Instead, it estimates surface temperature by detecting emitted infrared radiation. The interpretation of that temperature depends on how heat is being transferred within and around the component. For example, a large steel vessel and a small steel bolt may have the same temperature, but the vessel contains far more thermal energy because of its much greater mass. Confusing these concepts can lead to incorrect engineering conclusions. A practical example involves touching a metal handrail and a wooden handrail on a cold morning. Both may have the same temperature, yet the metal feels much colder because it conducts heat away from your hand much more rapidly. This illustrates that our perception of heat depends on heat transfer rather than temperature alone. Mastering these basic principles will make the remaining topics in this chapter much easier to understand, because every thermal image ultimately reflects the interaction between electromagnetic radiation, heat transfer, and material properties. In the next section, we'll examine exactly how heat moves through materials by conduction, convection, and radiation, forming the scientific foundation of infrared inspection. Now that we understand what infrared radiation is and the difference between heat and temperature, we need to examine how heat actually moves. Every infrared image is ultimately the result of heat transfer, so understanding these mechanisms is essential for interpreting thermograms correctly. This slide illustrates the three fundamental modes of heat transfer: conduction, convection, and radiation. Although they often occur simultaneously in real industrial systems, each mechanism operates differently and influences thermal patterns in its own way. Let's begin with conduction. Conduction is the transfer of heat through direct molecular interaction within a material. When one end of a metal object is heated, the atoms in that region vibrate more vigorously and transfer energy to neighboring atoms. The heat gradually travels from the hotter region toward the colder region. Metals are excellent conductors because their free electrons help transport thermal energy efficiently. Materials such as wood, plastics, fiberglass, and air are poor conductors, which is why they are commonly used as insulation. A practical example is a steam pipe. Even if the steam is contained safely inside, heat conducts through the pipe wall and reaches the outer surface, allowing an infrared camera to detect its temperature. If insulation is missing or deteriorated, the outer surface temperature changes noticeably, making the defect visible. The second mechanism is convection, which occurs only in fluids, liquids, and gases. Unlike conduction, where heat moves through stationary material, convection transfers heat by physically moving the heated fluid. Warm air becomes less dense and rises, while cooler air descends to replace it. This continuous circulation creates natural convection currents. Forced convection occurs when pumps or fans actively move the fluid. Convection explains why electrical cabinets require proper ventilation and why cooling systems are critical for motors, transformers, and electronic equipment. Restricted airflow often creates localized hotspots that infrared inspections readily detect. The third mechanism is radiation. Radiation differs fundamentally because it requires no physical medium. Every object above absolute zero continuously emits electromagnetic radiation, primarily in the infrared region. This energy travels through space and is what thermal imaging cameras actually detect. An excellent example is the sundae. Although space is a vacuum where conduction and convection cannot occur, solar energy reaches Earth through radiation alone. One common misunderstanding is assuming that an infrared camera sees heat moving through a component. In reality, the camera detects infrared radiation emitted from the surface. The internal heat transfer processes merely influence the surface temperature pattern that the camera observes. Professional inspectors must also remember that these three mechanisms rarely act independently. A hot motor housing, for example, transfers heat internally by conduction, cools externally through convection, and simultaneously emits infrared radiation toward the camera. Correct interpretation requires considering all three mechanisms together. Understanding how heat moves allows us to distinguish between genuine defects and normal thermal behavior, which becomes increasingly important as we study more advanced infrared inspection principles. Now that we've established the physics of heat transfer, we'll examine one of the greatest challenges in thermography, determining whether an observed temperature difference is real or only appears to be real. One of the most important skills an infrared thermographer develops is recognizing whether a thermal anomaly represents a genuine temperature change or simply an apparent one. This distinction separates experienced inspectors from beginners. An infrared camera does not directly measure temperature. Instead, it measures the infrared energy, or more precisely, the radiosity leaving a surface. Because many factors influence that radiation, not every hot or cold area represents an actual defect. Let's first consider real temperature changes. These occur because the component itself has experienced a physical change in thermal energy. Examples include friction generated by worn bearings, electrical resistance in loose connections, chemical reactions that release or absorb heat, phase changes such as evaporation or condensation, or direct heat transfer through conduction, convection, and radiation. In these situations, the component's temperature has genuinely changed, and the thermal image accurately reflects the underlying condition. Now compare that with apparent temperature changes. Here, the surface temperature may remain unchanged, but the infrared camera interprets the radiation differently because of surface characteristics rather than thermal conditions. The first influencing factor is emissivity. Different materials emit infrared radiation with different efficiencies. A polished stainless steel surface and an oxidized steel surface at exactly the same temperature may appear dramatically different on the thermal image simply because their emissivities differ. Reflectivity is another major source of error. Highly polished metals can behave almost like mirrors for infrared radiation. Instead of displaying their own temperature, they may reflect heat from nearby equipment, sunlight, or even the inspector. Transmissivity also affects certain materials. Some plastics, thin films, and specialized infrared windows allow infrared energy to pass through them. If the inspector does not recognize this behavior, the camera may actually be detecting radiation originating from objects behind the target. Geometry also plays a role. Sharp corners, curved pipes, and different viewing angles alter the amount of infrared energy reaching the camera, potentially creating misleading thermal patterns. Imagine inspecting a polished stainless steel pipe located beside a furnace. The pipe itself may be relatively cool, yet it appears extremely hot because it reflects radiation from the furnace. Without understanding reflectivity, an inspector could mistakenly report a non-existent defect. This is why experienced thermographers never rely solely on color differences. They evaluate surface condition, operating environment, material properties, viewing angle, and process conditions before reaching a conclusion. The examination tip on this slide reinforces an essential principle. Whenever a hot spot appears on a shiny surface, a repaired area, or an unusual geometry, question whether the anomaly is real before recommending corrective action. In professional inspections, confirmation using contact measurements, repeat imaging from different angles, or complementary NDT methods often prevents costly misdiagnosis. With this understanding, we're ready to examine the surface properties that govern infrared measurements, beginning with the single most important parameter in thermography, emissivity.
This slide introduces the 4 surface properties that every infrared thermographer must understand. Among them, emissivity is unquestionably the most important because it directly determines measurement accuracy. Let's begin with emissivity. Emissivity is the ability of a material to emit infrared radiation compared with an ideal blackbody, which has an emissivity of 1. A blackbody is a theoretical object that absorbs all incident radiation and emits the maximum possible infrared energy at a given temperature. Most industrial materials fall somewhere between 0 and 1. Rough, oxidized, painted, or non-metallic surfaces generally have high emissivity and therefore provide reliable temperature measurements. In contrast, polished aluminum, stainless steel, and other shiny metals have low emissivity, making accurate infrared measurement much more difficult. The second property is reflectivity. Whatever energy a surface does not emit may instead be reflected. Highly polished metallic surfaces behave almost like mirrors in the infrared spectrum, reflecting nearby hot objects rather than accurately representing their own temperature. Transmissivity refers to the ability of infrared radiation to pass through a material. While metals are essentially opaque to infrared radiation, certain plastics, specialized films, and infrared transparent windows allow some radiation to pass through. This property becomes important in specialized industrial and laboratory applications. Finally, we have radiosity. Radiosity represents the total infrared energy leaving the surface. It is the combination of emitted, reflected, and transmitted radiation. This is the quantity that an infrared camera actually measures. Understanding radiosity explains why an infrared camera is not a direct thermometer. The instrument measures total infrared energy first and then estimates temperature based on emissivity settings and other correction factors. The Level 3 insight provided on this slide reflects common field practice. When inspecting polished metal surfaces with emissivity below approximately 0.5, experienced inspectors often apply a small piece of high emissivity tape or a removable flat paint coating. The camera measures the tape rather than the reflective metal, dramatically improving accuracy without affecting the component itself. One frequent mistake during certification examinations is assuming that reflectivity or transmissivity is the most important surface property. In virtually every infrared inspection question, the correct answer is emissivity because it governs the relationship between emitted infrared energy and actual surface temperature. As inspectors gain experience, they quickly learn that correct emissivity settings are often more important than purchasing a higher resolution thermal camera. Even the most advanced instrument cannot compensate for incorrect surface property assumptions. With the science of surface properties established, we can now examine the equipment used to perform infrared inspections in both contact and non-contact applications. Selecting the correct measuring instrument is a fundamental part of any successful infrared inspection. Each device has unique strengths, limitations, and applications. The slide divides infrared equipment into 2 major categories: contacting devices and non-contact devices. Contact instruments physically touch the object being measured. Traditional thermometers are the simplest example, but industrial applications most commonly rely on thermocouples. A thermocouple consists of 2 dissimilar metals joined together. When the junction experiences a temperature change, it generates a small electrical voltage through the Seebeck effect. Electronic instruments convert this voltage into an accurate temperature reading. Thermocouples extend this principle by connecting multiple thermocouples in series, increasing sensitivity and making them suitable for detecting infrared radiation. Thermochromic coatings provide another interesting solution. These specialized coatings permanently or temporarily change color at specific temperatures, making them useful for monitoring equipment where continuous visual indication is desirable, or where reflective surfaces complicate infrared measurements. Now let's examine non-contact instruments. Optical pyrometers measure temperature from a distance by comparing emitted radiation, making them valuable for extremely hot objects that cannot be safely approached. Infrared thermometers, often called IR guns, provide rapid single-point temperature measurements. They are inexpensive, portable, and widely used for routine maintenance inspections. Infrared line scanners continuously monitor moving products on manufacturing lines, ensuring consistent quality without interrupting production. Finally, thermal imaging cameras represent the most sophisticated category. Unlike point measurement devices, they generate a complete two-dimensional thermal image called a thermogram, allowing inspectors to evaluate temperature distribution across an entire component. One important limitation should always be remembered. Point devices measure only where they are aimed. If you do not know the location of the defect, you may never detect it. Thermal imaging systems overcome this limitation by surveying the entire surface simultaneously. Professional inspectors often combine both approaches. A thermal camera first identifies suspicious areas, after which thermocouples or infrared thermometers verify the findings quantitatively. Equipment selection should always match the inspection objective rather than simply using the most advanced instrument available. Next, we'll take a closer look at one of the most widely used contact devices in industry, the thermocouple. This slide focuses on one of the simplest yet most reliable temperature measurement tools used throughout industry, the thermocouple connected to a multimeter. Although thermal imaging cameras receive most of the attention in infrared inspections, thermocouples remain indispensable because they provide accurate contact measurements for confirming thermal anomalies. The operating principle is straightforward. Two wires made from different metals are welded together at one end to form a sensing junction. When this junction experiences a temperature change, a very small electrical voltage is produced through the Seebeck effect. The multimeter detects this voltage and converts it into a temperature reading. Different thermocouple types, such as Type K, Type J, or Type T, are manufactured using different metal combinations, each designed for specific temperature ranges and industrial environments. The photograph on this slide illustrates a practical field setup. The thermocouple is placed directly on the surface being measured, while the multimeter displays the temperature. This arrangement provides an accurate reference value that can be compared with the thermal camera reading. In professional inspections, thermocouples are rarely used to search for problems because they measure only one point at a time. Instead, inspectors first perform a wide-area infrared survey, identify suspicious hot or cold regions, and then verify those locations using contact measurements. This verification process significantly increases confidence in the inspection results and helps eliminate errors caused by emissivity, reflections, or environmental influences. The common mistake highlighted on the slide is worth emphasizing. Attempting to inspect an entire motor, pipeline, or electrical switchboard using only a thermocouple would be extremely inefficient and would likely miss developing faults between measurement points. The examination tip also reminds us of two frequently tested concepts. A thermopole consists of multiple thermocouples connected in series, while thermochromic coatings change color at predetermined temperatures and are particularly useful on reflective surfaces. The best practice in industry is to combine the speed of thermal imaging with the accuracy of contact verification.
This combination provides both efficient fault detection and reliable temperature confirmation. Having examined contact measurement devices, we'll now move to one of the most common non-contact instruments, the infrared pyrometer and infrared thermometer.
Now let's move from contact temperature measurement to one of the most commonly used non-contact instruments in industry, the infrared pyrometer, often referred to as an infrared thermometer or IR gun. Unlike a thermocouple, which must physically touch the object, an infrared pyrometer measures the infrared radiation naturally emitted by a surface. The detector inside the instrument converts this radiation into an electrical signal, and the electronics calculate the corresponding surface temperature almost instantly. This allows inspectors to take rapid measurements from a safe distance, making the instrument ideal for hot, energized, rotating, or otherwise inaccessible equipment. The photograph on this slide shows a typical handheld infrared thermometer. Its simplicity often leads people to underestimate its capabilities. In reality, it is an extremely valuable screening tool used by maintenance technicians, electricians, mechanical inspectors, HVAC engineers, and process operators around the world. However, understanding its limitations is just as important as understanding its advantages. An infrared thermometer measures only a single point, or more accurately, a small circular measurement area determined by the instrument's distance-to-spot ratio. As the distance from the target increases, the measurement spot becomes larger. If that spot includes both hot and cold areas, the displayed temperature becomes an average rather than the actual temperature of the defect. This is one of the most common mistakes made in the field. An inspector may believe they are measuring a small, loose electrical connection when, in reality, the instrument is averaging the temperature of the surrounding conductor and terminal. Another major source of error involves emissivity. As discussed previously, shiny metallic surfaces emit very little infrared energy and instead reflect surrounding radiation. Pointing an IR thermometer at polished stainless steel or aluminum without correcting the emissivity setting can produce errors of tens of degrees. Experienced inspectors therefore verify three things before trusting any reading: the surface emissivity, the measurement distance, and whether nearby heat sources may be reflected into the instrument. The examination tip on this slide reinforces another important distinction. Optical pyrometers and infrared thermometers both provide single-point measurements. They do not generate images. Producing a two-dimensional temperature map requires a thermal imaging camera. In industrial practice, infrared thermometers are excellent for routine inspections, quick verification, and preventive maintenance rounds. When a broader understanding of temperature distribution is required, thermal imaging equipment becomes the preferred choice. Now that we've covered individual temperature measurement devices, let's explore the two major inspection approaches in thermography: passive and active techniques. This slide introduces one of the most fundamental classifications in infrared inspection: passive thermography and active thermography. Understanding the difference between these two techniques is essential because they are designed to solve different inspection problems. Let's begin with passive thermography. Passive thermography simply observes the natural temperature distribution of an object while it is operating normally. No external heating or cooling is introduced. The inspector measures the heat already being generated by the equipment itself. This is the most common form of infrared inspection used in industry. Electrical switchgear, transformers, motors, pumps, bearings, valves, boilers, and insulated pipelines are routinely inspected using passive thermography because faults naturally produce temperature differences during operation. For example, a loose electrical connection generates resistance heating, a worn bearing generates frictional heating, missing insulation allows abnormal heat loss. Since these conditions naturally create thermal anomalies, no artificial heating is necessary. Active thermography, on the other hand, deliberately introduces external energy into the test object. Heat may be applied using infrared lamps, flash lamps, lasers, hot air guns, or other controlled heat sources. After heating, the inspector observes how the heat flows through the material. The purpose is not simply to measure surface temperature, but to evaluate how internal features influence heat flow. Subsurface defects such as delaminations, voids, cracks, disbonds, corrosion, or moisture pockets interrupt normal heat conduction. These hidden defects alter the cooling or heating pattern, making them visible in the thermal image. The figure illustrates two inspection configurations. In reflective mode, both the heat source and the infrared camera are positioned on the same side of the component. This arrangement is commonly used when only one surface is accessible. In transmission mode, the heat source is placed on one side while the camera observes from the opposite side. Heat must travel completely through the specimen, making this method particularly useful for thin composite materials and certain laboratory inspections. One common misunderstanding is assuming that active thermography is always superior. In reality, the appropriate technique depends entirely on the inspection objective. Operating electrical equipment rarely requires external heating because faults already generate heat. Conversely, inspecting an aircraft composite panel for internal delamination often requires active thermography because the defect may not naturally produce a temperature difference. The examination tip reminds us that localized hot or cold regions appearing after controlled heating often indicate subsurface discontinuities because those defects disrupt normal heat transfer. As inspectors progress in infrared testing, selecting the correct inspection method becomes just as important as correctly interpreting the resulting thermogram. Now let's apply these principles by examining a real industrial thermographic inspection. Theory is important, but real competence in thermography develops when we learn to interpret actual thermal images. This slide presents a passive thermogram of a low-pressure propane storage tank, providing an excellent example of practical industrial inspection. At first glance, the thermogram appears to be nothing more than a colorful image. However, experienced thermographers understand that every color represents a specific range of infrared radiation and therefore a corresponding surface temperature. The image shows relatively uniform temperatures across most of the tank shell, indicating normal thermal performance. However, notice several distinct colder regions appearing as darker areas. These localized cold spots immediately attract the attention of an experienced inspector because they interrupt the otherwise consistent temperature pattern. Why would insulation damage produce a cold area instead of a hot one? The answer depends on the operating conditions. In this propane storage tank, damaged or moisture-saturated insulation changes the rate of heat transfer between the tank and the surrounding environment. As a result, the outer surface temperature differs noticeably from adjacent insulated regions. One of the most important principles in thermography is that inspectors rarely evaluate absolute temperatures alone. Instead, they compare similar regions operating under identical environmental conditions. Uniform equipment should generally display relatively uniform thermal patterns. Localized deviations often indicate developing problems. Another observation concerns the shape of the anomaly. Random isolated pixels rarely justify maintenance decisions because they may result from reflections, noise, or temporary environmental influences. Larger, well-defined thermal patterns extending across a physical region provide much stronger evidence of an actual condition. Environmental factors must also be considered. Solar heating, wind, rain, and recent weather conditions can all influence surface temperatures. Professional inspectors therefore document ambient temperature, operating conditions, weather, and inspection time as part of every thermographic survey. One common mistake is attempting to diagnose the exact defect from a thermal image alone. Thermography identifies abnormal heat patterns, not necessarily the root cause. Additional inspection methods, process information, or physical examination are often required before repairs are recommended. This case study demonstrates the true value of infrared testing. It provides early warning of insulation deterioration while the tank remains safely in service, allowing maintenance planning before significant energy loss or structural deterioration develops. In the next slide, we'll examine the numerical measurements associated with this thermogram and learn how experienced Level 3 inspectors interpret the findings. Now let's analyze the thermogram in greater detail and see how quantitative temperature measurements support the visual observations. The table identifies several measurement points distributed across the propane tank surface. Points 1 and 2 represent areas with temperatures between approximately 286 and 287 Kelvin. These values correspond to the normal surface temperature of the insulated tank shell under the existing environmental conditions. Now compare those values with points 3 through 6. These locations measure approximately 274 to 275 Kelvin, making them significantly colder than the surrounding surface. Rather than focusing on the exact numerical values, professional inspectors concentrate on the consistent temperature difference between neighboring regions operating under identical conditions. This cluster of adjacent cold points is the critical observation. When multiple neighboring locations all indicate the same abnormal behavior, the likelihood of random measurement error becomes extremely small. Instead, the evidence strongly suggests a localized physical condition affecting heat transfer. The Level 3 insight on this slide highlights an important inspection principle. A single isolated temperature anomaly may result from reflection, surface contamination, measurement angle, or instrument noise. However, a group of adjacent measurements showing the same trend provides much stronger confidence that the anomaly represents a genuine condition requiring investigation. In this example, the most probable explanation is moisture-saturated insulation or missing insulation. Wet insulation loses much of its thermal resistance, allowing heat transfer to increase locally. Consequently, the external surface temperature changes relative to the surrounding insulated areas. Notice that the recommended action does not immediately call for repair. Instead, professional practice requires confirmation. The suspected area should first be marked and documented using the thermogram. Contact temperature measurements, moisture detection, insulation removal, or visual examination should then verify the diagnosis before maintenance work begins. This systematic approach prevents unnecessary repairs while ensuring that genuine problems receive timely attention. Another best practice involves recording both the thermal image and the corresponding visible light photograph. Together, these provide valuable documentation for maintenance planning, future comparison, and inspection reports. Ultimately, thermography supports engineering decision-making by identifying where additional investigation should be focused rather than replacing sound engineering judgment. Having completed this case study, let's explore the wide variety of industries that benefit from infrared thermography. Having examined both the theory and a real inspection example, let's look at how infrared thermography is applied across modern industry. Perhaps the best-known application is electrical switchgear inspection. Loose terminals, deteriorated contacts, overloaded breakers, and unbalanced electrical loads all generate excessive resistance heating. Annual infrared surveys allow maintenance teams to detect these developing faults before they result in equipment damage, production loss, or electrical fires. Rotating equipment represents another major application. Pumps, motors, compressors, gearboxes, and couplings naturally generate heat during operation. However, inadequate lubrication, bearing wear, shaft misalignment, imbalance, or mechanical overload produce abnormal temperature increases that infrared inspections can detect long before catastrophic failure occurs. Insulated piping and pressure vessels are also ideal candidates. Missing insulation, moisture intrusion, damaged cladding, or deteriorated refractory materials alter the normal heat flow through the insulation system. These defects become visible as localized hot or cold regions, depending on operating conditions. Valves provide another excellent example. Internal leakage, restricted flow, or partial blockage changes fluid temperature across the valve body and downstream piping. Infrared thermography allows inspectors to evaluate valve performance externally without interrupting the process. Furnaces, boilers, and refinery heaters rely heavily on refractory materials to contain extremely high temperatures. As refractory linings deteriorate or thin over time, external shell temperatures rise. Identifying these hotspots early allows repairs to be scheduled during planned shutdowns rather than after emergency failures. Building inspections have also become an important application. Moisture trapped beneath roofing systems, missing wall insulation, air leakage around windows, and thermal bridges all produce characteristic temperature patterns that infrared cameras reveal quickly and non-destructively. Although the industries differ, the inspection philosophy remains identical. Every application depends on understanding normal thermal behavior, recognizing abnormal heat transfer, and correctly interpreting the underlying engineering cause. One important lesson from experienced inspectors is that thermography should never be performed in isolation. The most reliable conclusions come from combining infrared data with vibration analysis, ultrasonic testing, process monitoring, electrical measurements, or visual inspection. When multiple diagnostic techniques support the same conclusion, confidence in the maintenance decision increases dramatically. Now that we've explored where infrared thermography is used in industry, we'll conclude the technical portion of this chapter by discussing the most common mistakes inspectors make during field inspections and certification examinations. As we approach the end of this chapter, it's worth discussing something that often determines the quality of an infrared inspection, not the camera itself, but the inspector's understanding of the technology. Many inaccurate inspections result from simple mistakes that can easily be avoided with proper training and experience. This slide highlights some of the most common errors encountered in the field. The first mistake is confusing heat with temperature. We discussed this earlier because it is one of the most frequently misunderstood concepts in thermography and one of the most common questions in certification examinations. Remember, heat is energy in transit due to a temperature difference, while temperature is a measure of the average kinetic energy of particles. An infrared camera estimates surface temperature. It does not measure the total heat energy stored within an object. The second mistake involves emissivity. Many inspectors accept the temperature displayed by the camera without verifying whether the emissivity setting matches the material being inspected. This can produce significant errors, especially when measuring polished metals such as stainless steel or aluminum. Even the highest quality thermal imager cannot compensate for incorrect emissivity settings. The third mistake is drawing conclusions from a single thermal image. An isolated hot or cold spot does not automatically indicate a defect. Professional inspectors verify unusual findings by repeating the scan, changing the viewing angle, reviewing operating conditions, and when possible, confirming the result using a contact thermometer or another NDT technique. The final mistake concerns reflective or repaired surfaces. Fresh welds, replacement insulation, polished metal, or recently repaired areas often exhibit thermal behavior that differs from the surrounding material. Without understanding the component's history, these areas can easily be misinterpreted as defects. Experienced thermographers also pay close attention to environmental conditions. Wind can cool surfaces rapidly, direct sunlight can create temporary heating, and rain can significantly alter thermal patterns. These influences must always be considered before interpreting a thermogram. One best practice followed by Level 3 inspectors is to compare similar components operating under similar conditions. For example, comparing all three phases of an electrical connection or comparing identical bearings on parallel pumps often provides much more useful information than evaluating a single temperature value in isolation. Ultimately, successful infrared inspection depends on combining technical knowledge, practical experience, and critical thinking. The camera provides information, but the inspector provides the interpretation. Now let's review the type of interview questions you may encounter during certification or employment discussions. Technical interviews often focus less on memorizing definitions and more on demonstrating that you understand the engineering principles behind infrared inspection. The questions presented on this slide are representative of what you may encounter during certification interviews or job assessments. The first question asks you to explain the difference between heat and temperature. Rather than simply memorizing a definition, explain that heat is thermal energy transferred from a higher temperature region to a lower temperature region, while temperature represents the average kinetic energy of the particles within a material. Using practical examples makes your answer much stronger. The second question concerns emissivity. This is one of the most important topics in infrared thermography because emissivity determines how effectively a surface emits infrared radiation. An incorrect emissivity setting leads directly to inaccurate temperature measurements, regardless of how advanced the thermal camera may be. The third scenario describes a hot band across a valve seat. An experienced inspector would recognize that abnormal heating may indicate internal leakage, excessive flow restriction, or friction associated with valve operation. However, the correct professional response does not end with identifying a possible cause. It includes recommending confirmation using process data, contact temperature measurements, or additional inspection methods before maintenance decisions are made. The final question addresses repaired areas. Repairs frequently change material thickness, weld geometry, insulation condition, or thermal conductivity. These changes alter the normal heat flow and may produce thermal patterns that differ from the surrounding material even when no defect exists. Therefore, repaired regions require careful interpretation and often additional verification. During interviews, employers are evaluating more than technical knowledge. They want to see your inspection methodology, your understanding of limitations, and your ability to avoid false conclusions. When answering technical questions, structure your response logically. Begin by explaining the principle, describe its practical significance, identify possible limitations, and conclude with the appropriate engineering action. This approach demonstrates both competence and professional judgment. Developing this style of thinking is far more valuable than memorizing isolated facts because real inspections rarely present textbook conditions. With these interview concepts understood, let's reinforce the chapter using certification-style multiple-choice questions. This section reviews several multiple-choice questions similar to those used in ASNT, ISO 9000, 712, and other professional certification examinations. Rather than immediately selecting an answer, let's understand the reasoning behind each question. The first question asks about a limitation of infrared testing. While infrared inspection provides rapid, non-contact evaluation, repaired areas can alter heat flow because material thickness, composition, or thermal conductivity may have changed. These alterations complicate interpretation and often require additional verification. Understanding why this limitation exists is more important than memorizing the answer. The second question revisits the distinction between heat and temperature. This concept has appeared throughout the chapter because it forms the scientific foundation of thermography. Remember the simple rule. Heat is energy, while temperature is the measurement of that energy's intensity at the molecular level. The third question compares passive and active thermography. Passive thermography observes naturally occurring temperature differences without introducing an external heat source. Active thermography intentionally applies external heating to reveal hidden or subsurface discontinuities by observing how heat flows through the material. The fourth question concerns the three modes of heat transfer. Every thermographic inspection is influenced by conduction, convection, and radiation. Although infrared cameras detect radiation directly, conduction and convection strongly influence the surface temperature patterns that the camera observes. During examinations, many incorrect options are intentionally designed to appear plausible. Instead of relying on memory alone, think about the physical principles you've learned throughout this chapter. Understanding the science makes selecting the correct answer much easier. A useful examination strategy is to eliminate obviously incorrect choices first. This increases your probability of selecting the correct answer even when you are uncertain. Now, let's continue with the remaining certification questions, which focus on equipment selection and emissivity. These additional questions focus on equipment, surface properties, and blackbody theory topics that frequently appear in professional certification examinations. The first question asks, which instrument performs non-contact temperature measurement? The key principle to remember is that pyrometers and infrared thermometers measure emitted infrared radiation without touching the object, whereas thermocouples and conventional thermometers require physical contact. The next question asks, which surface property is most important in infrared thermography? Throughout this chapter, we've repeatedly emphasized emissivity because it governs how efficiently a surface emits infrared radiation. Incorrect emissivity settings directly affect temperature accuracy, making this the most critical parameter in practical inspections. Another question addresses the concept of a perfect blackbody. A blackbody has an emissivity of 1, meaning it emits the maximum possible infrared radiation for its temperature. While no real industrial material behaves as a perfect blackbody, this theoretical model provides the reference against which all other materials are compared. The final question concerns the practical recommendation of applying paint or high emissivity tape when the surface emissivity falls below approximately 0.5. This simple field technique significantly improves measurement reliability on polished or reflective metal surfaces. Notice that these questions require understanding rather than memorization. If you understand why emissivity affects temperature measurement, why polished metals reflect infrared energy, and how infrared instruments detect radiation, the correct answers become logical rather than something that must simply be remembered. One effective examination technique is to ask yourself whether each answer choice agrees with the basic physics of heat transfer and infrared radiation. When the underlying science is understood, certification questions become much easier to solve. Having completed the review questions, let's summarize the key lessons from this chapter. Let's take a moment to consolidate the most important concepts we've covered throughout this chapter. We began by learning that infrared thermography is a non-invasive inspection method used to determine surface temperatures and identify abnormal thermal patterns without physically contacting the component. Because many developing faults produce heat before failure occurs, infrared inspection has become one of the most valuable predictive maintenance technologies available today. We then distinguished heat from temperature. Heat is energy transferred because of a temperature difference, while temperature is the measure of the average kinetic energy of particles. This distinction is fundamental to understanding thermography. Next, we examined the three mechanisms of heat transfer: conduction, convection, and radiation. Although infrared cameras detect only radiation, all three mechanisms influence the surface temperature distribution observed during an inspection. Surface properties receive particular attention because they directly affect measurement accuracy. Emissivity emerged as the most important parameter, while reflectivity, transmissivity, and radiosity explained why infrared cameras measure emitted radiation rather than temperature directly. We compared contact measuring devices such as thermocouples with non-contact instruments, including pyrometers, infrared thermometers, line scanners, and thermal imaging cameras. Each has specific advantages depending on the inspection objective. We also distinguished passive thermography from active thermography. Passive inspections observe naturally occurring temperature differences, whereas active inspections introduce external heating to reveal hidden defects by monitoring heat flow. The industrial case study demonstrated that successful thermography depends not only on identifying thermal anomalies, but also on interpreting them correctly and confirming findings before recommending corrective action. Finally, we discussed common inspection mistakes, practical field experience, interview questions, and examination techniques designed to prepare you for professional certification. Remember one important principle above all others: a thermal image is only the beginning of an engineering investigation. Correct interpretation requires knowledge of heat transfer, material properties, operating conditions, and sound professional judgment. With these concepts established, let's conclude the chapter with one final review.
We've reached the conclusion of Chapter 12, and this final review provides an opportunity to confirm the knowledge you've gained throughout the lesson. The first review question asks about the 3 modes of heat transfer. By now, you should immediately recognize conduction, convection, and radiation as the complete answer. Remember that radiation is unique because it transfers energy without requiring a physical medium. The second question asks which instrument performs non-contact temperature measurement. The correct answer is the pyrometer, representing one of the most widely used portable infrared measuring devices in industrial maintenance. The third question revisits the most important surface property in infrared thermography, emissivity. Every professional thermographer understands that correct emissivity settings are essential for obtaining reliable temperature measurements, particularly on metallic surfaces. The final question asks about the emissivity of a perfect blackbody. The correct value is 1, representing the theoretical maximum emitter of infrared radiation and serving as the reference standard for all emissivity calculations. Although these review questions appear straightforward, they represent concepts that inspectors apply every day in the field. Understanding the science behind the answers is far more valuable than simply remembering them for an examination. As you continue your studies in non-destructive testing, remember that successful infrared inspection combines scientific knowledge with practical observation, careful interpretation, and engineering judgment. The thermal camera provides valuable data, but it is the inspector's understanding of heat transfer, material behavior, and operating conditions that transforms that data into meaningful maintenance decisions. Thank you for completing Chapter 12 on thermal and infrared testing. Continue practicing by analyzing real thermograms whenever possible, because experience remains one of the most valuable tools in becoming a competent infrared thermographer. In the next chapter, we'll build on this knowledge by exploring another important non-destructive testing method and its practical industrial applications.